Hi everyone, in this video I'm going to show you how to calculate the electric field of a uniformly charged ring. Let's get right into it. Okay, the first thing I'm going to do is draw the ring in question. So it's going to look like this, and it has a positive charge Q distributed evenly or uniformly. And let's say we want to calculate the electric field at some point in space out here, x, y, z. Now, what we do is we choose a random point on this ring, and we call it x prime, y prime, z prime. Now, if you remember from the introduction video, the electric field from this portion of the ring on xyz is going to be dE equals 1 over 4 pi epsilon 0 times dq over script r squared times r hat. Now, the script r here is the distance between the 2 points, and r hat is the unit vector in the direction from x prime, y prime, z prime to xyz. And in order to get the total electric field at xyz, what we do is we integrate over the entire ring here. So this is going to be the integral of dE, and if I bring the constant in front, that's going to be 1 over 4 pi epsilon 0 times the integral of dq over r squared r hat. Okay, so now, because the ring is a one-dimensional object, I'm going to replace dq with this is going to be a linear charge density lambda at x prime, y prime, z prime times ds prime. ds prime is the differential of arc length over r squared. Now, r hat, the unit vector, is the vector r over its magnitude r. Now, if you remember from a circle, the arc length is s equals r theta. So I'm going to call the radius of the circle here capital R, and because the radius is a constant, ds is going to be r times d theta. So I'm going to plug in r d theta prime for ds prime here. And because the charge density is constant, I can pull it out in front of the integral with the rest of the constants, and that will give me lambda over 4 pi epsilon 0, and now integral from ds prime, that's r times d theta prime, over r cubed times the vector r. This is the position vector from x prime, y prime, z prime to xyz. Now, because we have an entire ring here, the integral, the limits of integration are going to be from 0 to 2 pi. And the radius r is a constant as well, so I can pull that out in front. So this is lambda times r over 4 pi epsilon 0, integral 0 to 2 pi. And now I have to write the expression for r and the vector r and its magnitude. So the distance between these points, I take the vector xyz, and I subtract from that the position vector x prime, y prime, z prime. So we always subtract the vector that we're going to minus the from vector. So this here is going to be x minus x prime squared plus y minus y prime squared plus z minus z prime squared, and this is all to the this distance here is the square root here, like that, and this is cubed, and the position vector r is just going to be x minus x prime, y minus y prime, z minus z prime, and this is d theta prime. Now, in order to make this integral as simple as possible, it's always we generally want to choose a coordinate system in which the ring is symmetrical about it. So I'm going to choose the coordinate system like this. So the origin is going to be at the center. And these here are going to be my x, y, and z directions. I put these zeros here on the coordinate axes just to distinguish them from the point x, y, z, and from x prime, y prime, z prime. It would be I want to keep everything. I want to be able to distinguish between the point as well as the axes. So that's why I put zeros here on the axes. So in this coordinate system, z prime here is going to be 0 because the ring lies within the x naught y naught plane. So so that's one benefit of choosing this coordinate system here. And because we're integrating over a circle, x prime is going to be r cos theta prime, and y prime is going to be r sine theta prime. So if I plug in these relations here into this integral, lambda r over 4 pi epsilon 0, integral 0 to 2 pi, this is going to be x minus r cos theta prime, y minus r sine theta prime, z minus 0, because the ring lies in the plane. So this becomes just z, and now over. Now, if I combine the square root with this cubed on the outside, that's going to be to the power of 3/2. So in here, I'm going to have x minus r cosine theta prime squared plus y minus r sine theta prime squared, and then plus z squared to the power of 3/2 d theta prime. And the integral of a vector is in order to integrate a vector, we have to integrate its components. So I bring this integral into each one of its components. So this is going to be lambda r over 4 pi epsilon 0. And now integral 0 to 2 pi. And on top, I'm going to have x minus r cos theta prime over all of this here. So I'll just copy and paste that to save time. All right, and now it's going to be the same thing for the y, but with y minus r sine theta prime in the numerator. Oh, and there's also a d theta prime out here. And so y minus r sine theta prime over And for the z component, that's just going to be z over all of this again. Now, as you can see, these integrals here are particularly brutal. It would be necessary to use the methods of complex analysis to solve for them. And so what we do in introductory physics is we content ourselves with just finding the electric field on the axis of symmetry. So rather than finding the electric field at a general point x, y, z, what we do is we just want the electric field at a point on the axis of symmetry. So in that case, x becomes 0, y becomes 0, and z just remains as z. So with that, these integrals simplify considerably so that you can solve it using the methods from calculus. So in that, I'm just gonna so this formula here is for the electric field at a general point, that is at x, y, z. But now this here is going to be at 0, 0, z. So lambda r over 4 pi epsilon 0. So the numerator here becomes negative r cos theta prime. And the denominator, if we set x and y equal to 0, what we have here is negative r cos theta prime squared plus negative r sine theta prime squared. And that simplifies to just r squared, because cosine squared plus sine squared equals 1. So that simplifies very nicely. And this is d theta prime. And in the second component, I'm going to have negative r sine theta prime in the numerator. So this is negative r sine theta prime over, and it's the same story because in the denominator, so it's just going to be r squared plus z squared, and now d theta prime. And last but not least, we have the third component. So z here is just a constant, so I can pull it out in front. And this is just going to be integral from 0 to 2 pi d theta prime on top over r squared plus z squared. Oh, I forgot. This is raised to the power of 3/2. Can't forget that. Okay. So now this the denominator is not dependent on theta, so I can pull that out of the integral and out in front of the vector here. So this is lambda r over 4 pi epsilon 0 times 1 over r squared plus z squared, the 3/2. And now inside the vector, I'm going to have, I can pull the negative r out in front. So this is negative r times the integral from 0 to 2 pi of cos theta prime d theta prime. The second vector is going to be similar, but with sine. So this is sine theta prime d theta prime. And now the third component is just z times the integral from 0 to 2 pi of d theta prime. So the antiderivative of cosine is just sine. Sine of 2 pi minus sine of 0 is just 0. So this integral is 0. The antiderivative of sine is negative cosine, and negative cosine of 2 pi plus cosine of 0 is -1 plus 1. That's also 0. And this integral here is just 2 pi minus 0. That's just 2 pi. So this is 1 over r squared plus z squared to the 3/2 power. And 0, 0, 2 pi z. And I can bring out the 2 pi z out in front. The 2 pi will cancel with the 4 pi, so we'll just have lambda r over 2 epsilon 0. 1 over r squared plus z squared, 3 to the 3/2. And 0, 0, 1. Now, this here is the unit vector in the vertical direction. And because my coordinate axes are x0, y0, and z0, the unit vector in the vertical direction is z hat 0. So this is lambda r over 2 epsilon 0. Z hat 0 over r squared plus z squared to the 3/2 power. And some physics professors want you to express the final answer in terms of the quantities given. So if the total charge is q, then the linear charge density is going to be the total charge divided by the total length of the object in question. So the total length is going to be the circumference of the circle, which is 2 pi r. So the linear charge density here, lambda, is going to be q over 2 pi r. So again, it's the total charge over the total length of the ring. And then this is going to be r over 2 epsilon 0 z hat naught over r squared plus z squared to the 3/2. The r's cancel, so the electric field is independent of the radius. Oh, never mind. There's an r right here. It's just that these r's cancel. So what we're left with then is q over 4 pi epsilon 0. Yeah, that's right. And then z naught hat over r squared plus z squared to the 3/2. And this here is our final answer for the electric field at on the axis of symmetry. All right. Thank you all for watching. Before I end the video, I just made a mistake here. So at this point here, when I brought out the 2 pi z, I forgot the z as well. So there should be a z here in the numerator, and all the way to the end. So this final answer here will have a factor of z in the numerator as well. All right, that's the end.